go. So, James, hi. So you've already heard too much from me today, but I'm going to try and give this talk, as Heiko said, Enzo couldn't be here, so I have to give this one a little bit kind of vicariously. And so what I did was, what we were able to do is I was able to hop on a call with Enzo before this presentation so that I could get an idea of what it was that he really wanted to say and what his messages were about this project, because, you know, that was a collaboration between Deutsche Telekom and Grakn to actually make this project happen. So I may have to refer to the notes that I've got over here so that I can make sure that I sort of relay roughly the message. I'll try not to add too much bias, but you know what I'm like. So let's start with what we're trying to do here is build an expert system with a knowledge graph. That was the remit of this project. How did that actually come around? Well, first of all, the views and opinions expressed in the following slides are mine and not should be attributed to my employer, but these are through the words of Enzo, so we interpret that as you will. Now, I think I'm supposed to say something funny alongside these memes, but I don't really know what. This one is around the general use case that we ended up building out with Deutsche Telekom. And the use case is, right, they provide home broadband until they don't, until something goes wrong. And so they identified that this was an interesting area to start to investigate for an expert system to help their end users and to you know, improve their customer service provision. This one, I really don't know what I'm supposed to say at this point. So conversational agents, I mean, the idea in general is you think you're talking to a person, but actually you're talking to a machine, and that's about all I've got to offer you on this. Now, this is clear, because this one is how clearly Enzo perceives Deutsche Telekom users reporting their problems, okay? I think, as I said, these views are not the views of Deutsche Telekom. However, the problem is you know, it's very typical to get responses coming from users saying, my internet is not working, okay? And we need something a little bit more specific. We need to actually guide them through something to actually fix this. So how did this actually come about? So the idea is that Deutsche Telekom went through something of a journey led by Enzo that led them to a path where they were using Grakn and how they were going to start building with conversational agents. And they were working with knowledge graphs, and in their terminology that also included things like triple stores. They found them really difficult to use. I wanted to investigate how knowledge graphs could be used, particularly to focus in this context of conversational agents, because they saw that as like the low-hanging fruit that knowledge graphs were going to enable. So they decided that this Wi-Fi use case is an interesting proof of concept. It's sort of scoped. It's very tangible in terms of like what the value is to their customers that they can provide. So they started to settle on trying to build something for this. The idea is that there is quite a complex setup that's actually involved when it comes to actually supplying home broadband to the user. And you've got, you know, this broader system where we've got network components, so that's on the Deutsche Telekom side, the actual infrastructure that provides that broadband from the, you know, from the source. And you've also got the components inside the home, which is under the user's control, but maybe, you know, often provided by Deutsche Telekom, such as, for instance, the main constituent component there, I'm going to try and get my mouse across, is being the router and any settings and this kind of thing according to that. So you've got configurations that you need to manage of all of these things, but there's very clear division, and so we're working on the right side of this. We're working on the actual configuration of the user's kit rather than on the network component side. So there's these diagnostic points are the points at which we need to start. And this model, Enzo assured me, he's found to be very common, both not just in this expert system domain, but also in Bayesian networks. This is a well-known model for fault finding. And I mean, to be honest, it kind of reads like common sense. So it's no great surprise in that respect. But the idea is we've got some sort of diagnostic point that we're using to indicate what's going wrong. And we know that that connects to some sort of subsystems about which it indicates, and it may or may not indicate some specific or non-specific fault cause that we want to identify. And once we understand what that fault cause is, we can identify what are the remedial actions we need to take in order to fix them. So this is the goal. Resolve the problem by following this kind of meta model. Now, this is the spreadsheet that was the bane of our lives for the month while we created this project, because it turned out that up until that point, my understanding is that this sheet was used actually essentially as the production version of the source of knowledge used by customer service representatives at Deutsche Telekom in order to try and troubleshoot over the phone what the problems were with a user's Wi-Fi router. Now, this was incredibly hard to interpret because actually an absolute genius had encoded this Excel spreadsheet, let me tell you, because they'd essentially encoded a state machine into an, Heiko's laughing, he remembers how this was. They had encoded a state machine into an Excel spreadsheet. That was what we found. Now so we had, you know, we can see here, for instance, that all of the rows here are all relevant to just one particular router type, the speed port W701V. We're intimately acquainted. And we have here all of the different possible router LEDs that are available on these routers that actually have, you know, you normally just see them flicker and you think, are they red or are they green? Well, let me tell you, they can take an awful lot more states than that, and that determines an awful lot about what's actually going on. That is conditional on all sorts of other configurations that are going on within those routers. And so we thought, well, this is clearly an incredible use case, because the idea that someone has to manually pore over these things to try and deliver an answer to someone is clearly, you know, is clearly not maintainable and not scalable to any other kind of thing. So this is great, and we had this, but what we had there is this hard source of data that told us exactly what we need to fulfill for all of the different routers that they wanted to support for the project. So what are the actual initial requirements of what we wanted to build? Well, we wanted an expert system that was built around a knowledge base, that would have a data schema designed to support troubleshooting specifically, so, you know, develop that troubleshooting schema according to the sort of meta model idea that we had there, and any rules or constraints required to support it. So we're already anticipating that we're going to need logical reasoning for this. We needed also to support a logical flow of questions. The idea was that this should integrate quite seamlessly with the same, like, if you like, infrastructure that DT had already in place, which is service representatives talking to customers on the phone. So, you know, there's two possible ways that we can run this. You can either have the troubleshooting solution that we want to build actually accessed by the agent at Deutsche Telekom, or at least to start with, and then maybe if it's working well enough, maybe you can then actually let customers access that directly. But the general idea was we need to basically orchestrate the flow of questions that we need to ask the users in order to determine what their problem is and suggest fixes. So we have this flow of questions that mimics essentially what the operator would do currently, but in this rigorous fashion. And then the last point was to also then enable a chatbot dialogue to support that flow of questions, so that you could then you could either interface that chatbot to the customer service agent or to the customer directly. And so then we have some more specific requirements, because that's for troubleshooting in general. So what we had, there's a lot of talk in this about LEDs. So what we're talking about is literally just the flashing indicator LEDs that you have alongside a home broadband router, which indicate an awful lot about the internal state of what's happening in that router. But how they do that is totally dependent upon the model of the router. So it changes radically from one to another. So we then need to have also awareness of the solutions that we can point customers to that address all of the different possible issues that are underlying. And we need to also be able to track information collected from the user during the dialogue. So we need to essentially update the knowledge base as the user answers questions. And that could be either implicit knowledge. So for instance, the user telling someone, okay, my power LED is now green. Or it could be implicit. So that's things that we've already done in the past, or that we might be able to infer. Number four is the inference. So inference of the status of the router implied by things we know. Testing? Okay. If I already have a green DSL connection, then I know that the router is on, for instance. And number 5, a strategy to determine in which order to ask the necessary questions depending on where we are in terms of the information state. So how do we go about actually refining this thing? What are we working towards? So here, the major thing that Enzo, particularly his, if you like, vision for this, was to make sure that that knowledge base is used as it sounds, as we tend to advocate that it's used, as that central source of truth for the application that you're running. So what we want to do is to create a dialogue state which is a representation of all of the things that have been, for instance, already asked of the user. So we always keep recorded into the knowledge base the responses we got in the past from the user. The dialogue state can then, we can define these update rules to show how the dialogue state should change depending on what the user says. So this is kind of starting to sound like the state machine logic that we were talking about in that spreadsheet, where depending on where the user tells us they are in terms of the status of their router, we can start to determine where we should be going next. And what we want to do is to be able to have logical inference of the actions we should perform and how they map to the dialogue state that we're in. So it's kind words from Enzo, but what he found is that all 3 mechanisms can be implemented directly in Grakn due to its rule inference capabilities. So the idea here is that we've got a couple of slides together to talk about how we navigate around this thing. So if the first, what we're talking about here is this decision tree, or maybe decision graph, of how the user interaction moves. And so one of the first questions, essentially the first question we always need to know from the user, was actually, what is the model of the router that you have? Because without that information, we're pretty much blind because there were so many different router possibilities. So once that's answered, then we're honed straight in onto more specific possibilities. And what we might see is that there's, for instance, only one state in which this WL indicator, which I think indicates that you have like actually a full connection, if that is green, we can actually backtrack and understand that a whole load of LEDs can be inferred from as their state from that one. But we can go in the other direction as well. If we don't have any information, then the first question we'll ask is, well, what's the type of your router? The next question we'll ask is, what's the status of your power LED? Is it on, is it off, or is it blinking, right? Off probably means we're going to suggest that you check your power. On means you're doing okay. Blinking means wait a minute because it's still starting up. You know, and we'll see typically, and kind of fortunately, these routers are set up in this sensible way where you progress through these LEDs in some way, typically with some other edge conditions that tend to come around. But the idea here was that what was fundamental for Enzo about building this application was that this was really versatile and that you can move around between these states totally flexibly, so that the reason he was obsessive about this is because that for him is how you can make sure that you can scale this system to any kind of troubleshooting scenario that you encounter, which is not just this one, but any other one which may not conform to the same rules that the router diagnostics does. So we've got these navigation rules. That means we can figure out how to move in either direction depending on what we need to do, and we can flesh that out a little bit more with this diagram. So this is perhaps more like, and this is where you can see that I'm starting to call this the decision graph that we're making, where we start down one particular track. So for instance, we've got the power off at the beginning, leads you to solution A. I'm willing to bet solution A says make sure your router is on. So to make sure that the power switch on and the cable is plugged in, right? Check these 2 things. And then of course we need to backtrack, because we now need to actually we need to check the power LED again, because we need the user to say, okay, now is it working? If it's not working, okay, do something else. So if they then tell you it's blinking, then you say, okay, well, what about these next scenarios? And when they hit a problem, we need to go back again and make sure that, okay, is that LED you told us about before, what's it doing now? And based on what it's doing now, we either need to offer you another solution, or we need to make sure that you actually step all the way through to actually having an active connection. Because actually the user might not just have one problem they encounter, they may have one problem on one branch, come back to the main trunk that we need them on, and then end up in a different direction and have to troubleshoot as they go. And so what we can see here is, for instance, if you provided the fact that the D LED was green, we can immediately know where you are in the tree, as long as we also know that you've got that particular type of router, because there's no other circumstance in that tree where the D LED is green. So we can infer straight away where you are. And so that is the way in which this is unlike a typical state machine, where you only have the state that I'm currently in and where I can transition to. We can dynamically determine the state based on the user-provided information. Really important to Enzo, I know, about to be able to architect something with that. So we have the model. I'm going to enlarge that a little bit. This is when Enzo and I talked about this, he made a really interesting point about this. He said, I said, why do we want to show this? And he said, this is to demonstrate how the characteristics of the system look. So to try and elaborate a little bit, what we've got up here is we have the idea of that's the name of the routers. This is the router up here. This is the diagnosis object that we have. This is our old visualizer, by the way. This whole project is a little bit outdated. You're going to see some old school Grakn from over a year ago. So that's actually I believe that might even be a relation that's actually being held here, because we're at the schema level. So that's a relation here which links to all of the different types of LED that you could have on the routers. So that's why we've got this particular structure that's coming up in the middle there. And then around the edge, what we see is how we encode the solutions that are provided to the user. So for instance, check your power cable, check your on-off button. You know, this thing would be one sort of checklist that ends up in this solution space over here. But Enzo's insight here was, this is a really complex scenario that we're trying to model. And he said, what is amazing about this is how clean the model actually can be and how clean that can look. So yes, it's still complex, but it's clean. There's no mess here. We can look at it, we can understand exactly what's going on, and we can work with that despite the complexity. That's what he saw as the major insight from something like this. So I mentioned this diagnosis relationship. This is the second hour I spent talking about diagnosis relationships today, but this one's a little bit further back in time. But this one, what we're saying is we use this one relation as essentially the tracker of the state that we have in the machine at any given time. So this is where we end up holding the state of what we should be doing and where we are, because we have this ongoing diagnosis that we're concerned with. So it holds all relation relating to the state. So in particular, it connects a router subject. So that's the router that we're diagnosing. Information about the LED statuses is collected from the user so far. And we also have some sort of user session identifier. And the main thing that we have here is the action. So the action is a role, where the role player of that action is inferred based on the dynamically assigned state of the system. So what we do is we look and we say, okay, based on the fact that we know the name of the router, what is the next question we should ask the user? The next question we should ask the user is about the power LED. Okay, now we know that when the user then responds to that question about the power LED and tells us the power is off. We say, okay, what's the next thing we should do? Well, the next thing is we should go to this action. So we have some more schema here. I'm not sure if it's actually that interesting to walk through the schema. And so once we've selected what the next action should be, right, the user goes and fulfills this, and then we dynamically understand where we are next in the procedure. So here we have what's interesting here is how we actually go about defining the dynamic understanding of the state of where we are. So here what we have is how you would insert a router. So up in the top corner here, we would say add a new router. And this is how, one of the major requirements here was to be able to flexibly add new pieces of hardware to such a system without that being too much of an overhead in terms of the programming. You didn't want to have to overhaul the whole system based on the fact that you've added just one new piece of hardware. So it's quite simple to add a new router by just inserting it with its given name and all the different types of LED that's associated with that router. And then what we have here is just one example of a rule. So this rule would say, given that we have a diagnosis of a router, where that router is the model speed port 10,000, that's a real thing, and that router has two indicators in particular states, where those states are green. We have another one. This is actually predates having negation in Grakn. So we had to insert negative facts. So we had, if the O indicator is unobserved, and we've inserted it as unobserved, then the next thing we shall advise is that as a then consequence of the rule, that the next action that should be taken in the diagnosis is to tell the user to look at that unobserved LED. Right? Now, that's just a simple one. That's just the one saying, look at the next LED. Okay, if you're in a good state, move to the next, look at the next LED and continue. And otherwise, this may point you in all sorts of other different directions according to your action. But crucially, the idea here is this, because it's done as a rule, this is what means that it applies dynamically, and therefore, this was actually one of the most intensive applications we've run, or at least at that point we had run with Grakn, where we had about 400 or so rules in the database that really stress tested the reasoner to be able to quickly rule out any rules that did not apply in the current circumstances. And so this is the query that you would then use in order to query for the next action. Now that we have negation, we'll actually be able to revisit this kind of system and get rid of all of this, where we had to query for things where the state of things was unobserved and that had been inserted, which is quite exciting. But this is just the one query that you would need to make in order to say, what's the next thing I should be doing? And the idea here is that if we've got this router, which has all of these attributes, and those are the states that we know and the inserted states that we don't know. If over here is our diagnosis relation, then the idea is that that action role points to whatever it is that you should be doing next concerning the router. If it's an LED, you should be checking. And I don't think I'm going to skip this one. This is how we would, this is a quick query that we would use to determine what are all the possible states of the LED that we might see, because we need the user to pick from a list and not just write in free-form text about what that thing is doing. And then what we also see is, again, with the same diagnosis object sitting down in the corner there, we can have that pointing to actions which can be some set of solutions that needs to be performed by the user. So another big requirement from Deutsche Telekom was to be able to have language drivers that were easy for them to use, specifically in Python, because a lot of their staff already work in Python. So this is just an example to show that this is some of the real code that we had operating to fulfill this POC. Natively in Python. Actually, there was some interesting stuff that we did there in terms of using templating engines to actually write our Grakl queries, because actually what we needed to do, we needed to write a lot of queries, and we needed to programmatically insert rules into Grakn, so we used a templating engine to try and alleviate some of the stress of that. And so what we have as some outcomes is that you are able to upgrade the model easily. Now, this sounds trivial in this scenario, and we'll talk in a couple of minutes about some of the lessons learned and what Enzo understands of the other options that you have and why they can fall down in these kinds of regards. So being able to add new routers, Speedport is a kind of router, can be added and deleted at any time dynamically from the knowledge base without a problem, because the knowledge base is just being used as the source of truth here. The application doesn't have to do anything too fancy. And overall, the architecture we actually built was to also build this Slack bot on top of the knowledge base, so we would have that Python interface sitting in between to just do rudimentary logical operations to make the queries to Grakn, and then to serve the results of those queries to the Slack bot that would prompt the Python. So what we would end up with is we unfortunately were not able to give a demo today, but we had this live. In fact, I think it sounds like, because the project was over a year ago, Slack's been updated since, and we couldn't actually manage to get this thing to come back to life. But what we'd have is we have this bot called Router Helper, and you can see it's got a little Grakl bot to it, and it says, "Hi, rest assured, we will help you with your router-related problem." And we actually just had to map out a few different scenarios that you would want to pick. You'd pick a scenario, and then you would have this, you would have this back and forth with the chatbot where it would give you a checklist of all the different possibilities of what could be happening right now. You pick the most appropriate one, and then it tells you where to go next. Whether it's resolving an issue and keeps essentially pushing and pushing through that graph of possibilities until it finds that all of your problems have been solved and you've got walk away very happy with your working home internet connection. So I know that Enzo particularly wanted to make points about the lessons learned, the tools, their understanding of the space that he got from doing this, from this project, and also even before running this project, why he ended up going about it in this way. And I mean, at this point, I could say whatever I want, but I really am actually reflecting the words that he told me over the phone. What he found was that he said that the knowledge graph implemented through Grakn is extremely powerful and flexible, a great tool to implement such an expert system, really easy to model and implement, and the expert system and fault finding system worked really well through a conversational agent. So that's all great. So what about the downsides, though? He's got some really interesting insights on this. So what his lesson learned, one of them at least, was that he calls it the knowledge representation impedance. I've got quite a lot of notes on this. So what's really interesting about his insight here is he's saying how much does actually for instance, in Grakn, knowledge representation, he speaks very highly of. And we can make efforts to make a really nice, rich model. And what that does is that means that our querying becomes really trivial compared to other systems. But there's people on the other side of the fence that will just throw all of their data into RDF triples and have the nightmare instead on the querying side rather than on the modeling side. So that's where they will spend their time. And so there's a way up, essentially, here that he sees as to which way you decide to go. And what he says was in particular that if you essentially have this way up of, for instance, doing things that Grakn way, or what he saw as the other major option, the other major adversary to this approach, which another team in Deutsche Telekom looked at, was storing the dialogue state and rules into some sort of variable slots in a conversation. So there's some sort of script to the conversation, and there's variables that can go into there. Now, what he described is that there's a huge downside to this, particularly because you're not following the same knowledge-based model that he wanted to use for this kind of platform. Because what it means is that the knowledge state that you have actually is somewhat implicit in the conversation structure that you define. Because if you leave slots in your conversation, which is where you can expect the user to say certain things or the bot to say certain things back, you're implying how your conversation is actually going to flow. And the problem with this is that this is really hard to scale and maintain because you don't have one source of truth about all of your model that you can access. You're actually now, when you add some new router, you may need to revise all of your conversational flow and also the data that you hold in the back end at the same time, because actually your knowledge is split between those two. And what you're totally disabled from doing is being able to make any sort of reasoned conclusions based on rules or otherwise logical conclusions across the two, because you have no cohesive system to link the two. So of the two approaches, he very much sat on this side, but it still remains that we still have this knowledge representation impedance that he found is still the downside to going in the way of trying to adopt Grakn in their business, where the problem is, he says, we don't have the rules to cover the landscape beyond the home/router subsystem. It's actually kind of surprising, right? Actually, what they have the rules for, and they know how it works, is actually the side that's in the homes of their users. But actually, the cost of finding the rules for the other subsystems seems very high. And in some ways, this makes sense, right? Because actually, what's going on in the home, it's mostly just around the cabling to a home broadband router. What's on the other side is all of the infrastructure that is hosted by Deutsche Telekom and run by them, or run, third party or whatever it might be. Some hugely complex system is sitting there, and actually how do we find and uncover the rules relating to that system? And this is where, so at the global system level, essentially, they're dealing with uncertainty, partly because of the variables within their own organization and how that, their tech stack and their hardware is actually structured. And so, in particular, I know that Enzo is very keen, loves the cleanness of the rule-based system, but believes that the practicality is that that's very hard to implement at really large scale unless you've got that systemically in the organization, in which case maybe the fault-finding system needs some sort of hybrid between rules plus some sort of probabilistic Bayesian network style system, and really wants to see the interplay, again, a bit of a theme, certainly from my day, I don't know about yours, between logical rules and probabilistic or machine learning or otherwise kind of methods. So, I think that's enough from me on trying to live vicariously through Enzo. I think probably I should reorder the thanks slightly and not thank myself at this point. So thanks very much to Enzo. It's really it's a real shame that he couldn't be here to present this himself today, and also to Klaus. Klaus worked really closely with us on this project, and to Heikel and Thomas also. A bit of a joint effort of the five of us to pull this together, but we were really glad to see this come around. So, within the scope of what I can answer as Enzo, please go ahead and ask any questions that you might have. Do you want to host questions, Heikel?
Is it? Okay. Should I use? Yeah. Yeah. So actually, you answered my question in your last part, but still, maybe you can elaborate. So if you would do it today, I guess you would use the KJ-lib to infer rules. So for the business side, that you work the experience from the field back into the knowledge graph.
Okay, so your question is, can we use, for instance, something like KG-lib to actually infer the rules that would go into the expert system? So that's actually we're not able to yet. That we don't necessarily see as the role of a knowledge graph convolutional network, because essentially what you're trying to do is then when you use an ML model, you're essentially trying to make a model that the learner understands of your system. And what you actually want as an outcome is a symbolic model or set of symbolic models, that is rules, as an outcome. So I think actually in terms of rule mining, which is a really relevant question, thank you for a project like this, if you've just got the data, right, of what worked and what didn't, maybe you can find a correlation that actually tells you what underlying to your system is the cause of the faults and therefore the remedies that worked and these kinds of things. It's perfectly suited to that. I actually don't think that the solution is probably a machine learning based one. If it is, it's some sort of adversarial network or something like this. It's not actually a straight up classic supervised machine learning problem. It's more likely to be a heuristics based symbolic logic sort of a project, which also falls within the remit of the KG-lib infrastructure that we're trying to build around research projects on top of Grakn. Any more, Freddie Moore? Alrighty, I'll hand it over to Heikel.